Hello, so today I'm going to be working on problem 8 from the midterm exam 1 for 2025. Start off by explaining the problem statement and kind of what we're going to be identifying. So it starts off by a ball and socket joint at the end of a rocker arm has a carbon steel spherical surface with a diameter of dB, which is equal to 10 millimeters, fitting in a phosphorus bronze bearing alloy spherical seat with a diameter of ds, which is equal to 10.2 millimeters. The problem is asking for us to find the maximum force so that the shearing stress from in the rocker arm from the contact stresses do not exceed 500 megapascals. Initially, doing this problem while taking the exam, I actually ran out of time to even do the problem. I wasn't able to get to it and identify what steps I could take to solve for the maximum force in the shearing stress. So that was the main thing when going back and identifying what needed to be done. Just kind of breaking down the problem step by step and really understanding it. So first, I'll go back and pretty much highlight some of the key points in the problem statement that I identified. So the first point is that the spherical ball, the ball inside the red ball right here, actually is a carbon steel spherical surface, and it has a diameter of 10 millimeters, and it's fitting inside of the socket, which is a phosphorus bronze bearing. And it has a diameter of 10.2 millimeters. Like I said, the problem statement gives us the maximum shear that it cannot exceed, wrong way, it cannot exceed 500 megapascals. And we are trying to find the F max for the problem. So identifying the problem and kind of understanding now that it is a contact stress problem, since we know that the two spherical surfaces are in contact with each other. And now pretty much, now that we know the problem and understand that it's a contact stress problem, we can come down here to the key equations that we can use. And the first equation is this radius of contact equation, which pretty much is the radius of the circular arc formed when two different spheres are pretty much in contact with each other, or objects come into contact with each other. And this equation pretty much just uses the force that we're trying to find. I'm going to highlight in yellow just real quick. And it pretty much just uses the ratio and the different Poisson's ratios and the elastic moduluses of each of each metal given in the problem statement, and then divides it by 1 over the two different diameters in the problem, which we are given in the problem statement. Next, since we also know that it is a contact stress problem, we know that it's going to have a pressure max at the, typically, is going to be at the center point, center point of contact. That equation gives 3F divided by 2 pi times the radius of contact squared. And actually, the last equation can actually be read from a chart, which is actually over here. I already have a little bit written out, but pretty much a breakdown of the chart. It gives pretty much a ratio, an understanding of the correlation between the P max, the pressure max right here, and what we're looking for is the max shear. And so if we come over here to the chart, we could see that this is the max shear line, and this actually correlates to the maximum pressure, which is going to have a shearing max equal to zero point 0.3 of the P max. And now that we kind of understand the relation and found a way to correlate the two equations, we can actually solve for the force in the maximum force that's needed to not exceed 500 megapascal. So now that we have identified our key equations that we need to solve the problem, we can go back into the problem statement and kind of identify some of the things that we need to solve the problem. So we know that it's carbon steel ball, and it's a phosphorus bronze socket. So that gives us our Poisson's ratio, our elastic modulus for both of them. So we can go over here to the chart, and identify where carbon still is. So right here, where I underlined, gives you the elastic modulus in gigapascals, but we can convert it to megapascals by multiplying by 10 to the third. And then we are given our Poisson's ratio for carbon steel of 0.292. Then we can come down to phosphorus bronze, which is the socket, and we are going to identify the 111 times 10 to the third megapascals, and then the Poisson's ratio that's needed. And then we were also already given the diameters of the ball and the socket opening from the initial problem statement. So now we can use the equations that we have. So the shearing max, we know is 500. So we set it equal to 0.3 of P max to solve for P max that we can later use to plug into the problem. And we identified that the P max is going to equal to 1,666.67 megapascals. So to make it easier to solve for F in the equation, I pretty much use this P max equation and set it equal or solved where it's equal to A. And it's going to be A is equal to the square root of 3F over 2 pi of P max. And to make this easier also, I pretty much just initialize this first equation as equation 1 and this new equation that I solved for as equation 2. And as you can see in this problem statement, I pretty much explained that I set the two equations equal to each other to solve for F. And so first I started off, we know our Poisson's ratio, our elastic modulus for each, and our diameters that we need. So now it's just solving for F. So once I pretty much plugged everything in on the right side, all of these, the values that I needed. Then I pretty much came down here. And to make this easier, we obviously see that the F is in the square root. So we know that the square root of F is going to equal F equal to the 1/2. So you can pull that out and pull it in the front to make it easier to just solve for F in the problem statement. And we can also do the same thing for this one because we also know that the square root to the third of F is equal to F to the 1/3. So after solving for everything in the parentheses and here in this equation, we get the answer of 6.22 times 64 times 10 to the negative fifth. And we pretty much are taking this whole thing and the P max that we plugged into the equation and dividing the F's to get on one side and all the numerical values all on one side. And we already know once we divide the F of 1/2 divided by the F of 1/3, it's pretty much just subtracting the exponents, which gives you F to the 1/6. And once we end up solving for the numerical values, we get that this numerical value is going to equal 1.6886. And after that, we obviously understand what the F is going to equal to. It's going to be 1/6. F to the 1/6 is equal to 1.6886. And you're pretty much going to just take the exponent to both sides. You're just going to put it to the 6th power to identify what your F value is going to be. So once you do that and once you identify that, you pretty much get that your F value is going to equal 23.187 newtons. And that is the maximum force that the part can withhold before shearing stress exceeds 500 megapascals. And you can actually check your answer by first plugging in your F into the first equation, the radius of contact, and then plugging in your F and your A that you just solved for into your P max, and then finally plugging in your shear max equal to your 0.3 of P max, and that's going to give you your final answer that it is actually equal to 500 and it does not exceed 500. So